Welcome to Module 2, the sound wave. In this module, we will deepen our understanding of acoustics and the properties of sound waves. In this module specifically, we will explore the fundamental aspects of sound waves, their behavior, and their implications in audio technology. Sound waves are created by repeated compressions of air particles. So, for example, a vibrating guitar string compresses air particles, generating a wave that travels to our ears. This movement creates pressure variation around the atmospheric baseline, forming the wave we perceive as sound. You can see this process in the animation. Instead, in this video, we generate a sine wave. We can actually hear that the sine wave visually actually is a sine function and correspond to a sound. From the mathematical point of view, sound waves are defined by some key properties that you can see in the graph. So the first is the peak level, which is the highest value on the wave. The peak-to-peak level, which double the peak level in symmetric waves. And then the period, which is the time to complete one cycle. The wavelength, that is the distance the wave travels during one period. And then the frequency, which is one of the most important parameters for us. That is measured in Hertz, and it represents the number of cycles per second. A higher frequency means a higher pitched sound. The last parameter is the phase, that refers to the wave's shift in time or space. We measure this in degrees or radians. As we will discuss later in greater details, phase differences between waves are critical for understanding sound interactions. So now, when multiple simple sine waves combine together, they form a complex wave. These waves better represent the natural sound. The combination can be done by the sum of amplitude values for each wave for each time instant. In the video, we have 3 sine waves at different frequencies. By summing them, we obtain a complex wave. The sound of the resulting wave that we can hear is the same that would be obtained by playing the 3 single waves together. Sine waves are simple to manage. Complex waves are not. So now let's ask to ourselves, is there a relationship between the sounds we hear around that are complex wave and the sine wave that are simple? If so, the process of analyzing and processing sounds could be simplified. We could in fact always refer to the sine wave or to the composition of sine waves. Charles Fourier demonstrated that even the most complex wave can be expressed by the sum of a set of simple sine waves through the Fourier transform. Each sine wave has its own amplitude, frequency, and phase. This concept underpins sound analysis and processing. Let's move now to define the single characteristics of sine waves. The first is the waveform that shows the amplitude of a sound wave over time. It visually represents how loud or soft a sound is at any moment. So for instance, a waveform of a drum hit would show a sharp, high peak, followed by a decay as the sound fades. The second parameter is the frequency. And the frequency and the wavelength are connected and they are inversely related. Using the speed of the sound air, approximately 340 meters over a second, we can compute the wavelength. And here are some formulas that connect the frequency half, the t, the period, L, the wavelength, and V, which is the speed of the sound, which is 340 meters over a second. So the frequency is 1 over t, and the wavelength L is computed by v over f. On the other side, f is v over L, which is basically 340 over L. And then L is v over 1 over t, which is basically v, the speed, multiplied the time, so the period. So let's now provide some example. So let's consider to have a sine wave at 500 Hz. The wavelength is about 0.68 meters. Indeed, since t is 1 over f and is basically 0.002 seconds, L is computed as 340 multiplied 0.002 seconds. This result has 0.68 meters, and we proved it. Equivalently, we can compute it using another approach, and basically we can say that L is 340 meters over second divided by 500 Hz, which is, as a result, 0.68 meters. So we proved it again. So let's talk now about another important parameter, which is the spectrum, which is a graphic representation that displays frequencies on the x-axis and their intensity on the y-axis. In particular, there are frequencies and amplitudes of a single sine waves extracted by the Fourier transform. Each bar or beam represents a frequency range. Increasing the number of beams improves the resolution, allowing for more precise analysis. And this is crucial for identifying the fundamental frequency and harmonics of musical note. Yeah, since there is a very strict connection between the musical notes or musical pitches and frequency. This relation in particular exploits that the musical notes correspond to specific frequencies, which is the higher peak in the spectrum, if any, and we can see it in the graph. We can recognize, from the perceptual point of view, a musical note because we are able to recognize the frequency of the higher peak in the spectrum. So, for example, the note A4 has a frequency corresponding to 440 Hz. Now, if we consider a note and we double the octave, so we double the frequency. This exponential relationship underlines how we perceive musical scales and harmonies. As a consequence, our perception of note frequency association is based on an exponential and nonlinear function. Hence, our sensitivity to distinguish nearby frequencies decreases as frequency increases. Therefore, in the spectral representation, frequencies are displayed logarithmically. You can see it in the plot, where the graphical distance between 30 and 70 Hz is the same that separating 1.8 kHz and 3.7 kHz. An evolution of the spectrum is the spectrogram, which combines frequency, intensity, and time into a single visualization. This is important since the audio and the sound is evolving in time. So the intensity is expressed with the color intensity. It provides a comprehensive view of how sound evolves, helping us analyze dynamics like pitch changes and intensity variation over time. And now let's move to the last characteristic of the sound waves, the phase, which is defined as the instantaneous value the sinusoid assumes in its initial state. Now, we can consider the sinusoid as a circumference. In this scenario, a specific position on it can be expressed by an angle. So phase is crucial in sound wave interactions. So in fact, in acoustic, we are more interested in times and space since travel. So for this reason, we express the phase as the temporal or spatial shifting on a sine wave with respect to another. Two waves are in phase if they are temporally aligned, out of phase if they are temporally misaligned. In this figure, for instance, the second sine wave is shifted with respect to the first by 1/4 of the wavelength or period, and so on. If the wavelength is 0.1 meter, so then the second sine wave is shifted with respect to the first of 0.025 meters. So, Two waves in a phase amplify each other, while waves out of phase can cancel each other, create a comb effect. For example, phase cancellation occurs when two waves at the same frequency are 180 degrees out of phase, resulting in silence. Understanding phase is vital for tasks like audio mixing and speaker placement. In the video, we can see initially the two waves in phase. We then move the second one by half of the wavelength, and we notice a great reduction of the volume. This is also evident in the second video, where the third plot depicts the sum of the two waves. The fourth plot instead represents the spectrum. Let's consider now some examples. So the first, let's consider to have a couple of waves at 500 Hz. A phase difference of half period, which is 1 millisecond, causes cancellation. Seconds. So given a couple of microphones and a sound source, the two microphones capture the same sound, but with a delay. If we approximate the distance to 5 centimeters, we will have a phase cancellation for a wavelength of 10 centimeters, which is basically f equal to the speed of sound over 0.10, which is resulting of 3,400 Hz. Third examples. Delayed sound sources with a delay of 5 milliseconds causes a comb effect at frequencies around 100 Hz. To obtain such result, we must find the frequency for which t, the period over 2, is equal to 0.005 seconds. It can be computed as f equal to 1 over the period multiplied 2, which is basically 100 Hz. By controlling the phase alignment, we can achieve desired audio effect or prevent unwanted interference. Frequencies around it are also affected. This is called the comb effect because the cancellation repeated along the spectrum. The comb effect is evident in the first video you can find here, where they use a sound with almost flat spectrum, which is the white noise. Moving the second wave, we notice the creation of several holes in the spectrum. This is very evident also in the second video. Let's move now to the conclusion of the module. In this module, we covered the fundamental properties of sound waves, from generation to interaction. These principles not only deepen our understanding of acoustics, but also form the backbone of modern audio engineering. In the next modules, we will explore advanced applications, including digital sound processing. Thank you for your attention.